All right, let's talk about the future of AI. Because right now, there's a revolution happening in the very hardware it runs on. We're talking about a complete reinvention of the computer chip, one that's designed to solve AI's single biggest problem by learning a few tricks from the human brain.
So here's the issue, right? AI models are getting exponentially more powerful, which is amazing, but they are incredibly hungry. I mean, the sheer amount of energy it takes to train and run these massive networks is just staggering. We are literally hitting a hard physical wall, and the very architecture of our computers is what's holding us back.
And the main villain in this whole story is something engineers call the memory wall. See, for the last 70 years or so, computers have always kept their brain, the processor, and their memory separate. This creates this constant internal traffic jam where data is just shuttled back and forth, back and forth. Imagine a master chef who has to run to the pantry for every single ingredient, for every single step of a recipe. Well, it's that constant running around that wastes up to 90% of the energy in our modern AI chips. It's crazy.
So, to tear down that wall, researchers are looking at the most efficient computer ever known, our brain. And this has led to a huge paradigm shift called analog in-memory computing. It's this really revolutionary idea where the computation happens right where the data is stored. You just completely eliminate that wasteful back-and-forth travel.
But, okay, what does analog actually mean here? And how is it so different? Well, think of it like this. Digital computing, the kind we've used forever, is like a light switch. It's binary. It's either on or off, a 1 or a 0. That's it. But analog computing, that's more like a dimmer switch. It can represent a whole smooth continuum of values, and this allows a single tiny component to store much richer, more nuanced information, which, it turns out, is perfect for representing the weights in a neural network.
What's really cool is how this new method uses fundamental physics as a kind of shortcut. So instead of all this complex digital logic, it leverages Ohm's law, that relationship between voltage, current, and resistance, to perform multiplication almost instantly. At the exact same time, it uses Kirchhoff's current law to handle all the addition. What this means is that thousands or even millions of calculations can happen all at once, in parallel, just by using the natural laws of electricity. It's basically computing at the speed of physics.
But to actually build these new brain-like chips, we need a totally new kind of memory, one that can act like that dimmer switch. And right now, there's this fierce competition brewing between 3 key technologies. Each one is vying to become the foundation for this whole new era of AI.
So, first up is flash memory. This is the same stuff you have in your phone or in a solid-state drive. In this race, you can think of flash as the precise veteran. It's a mature, it's reliable, it's a technology we know really well, and it's just been cleverly adapted for this new analog role. So, flash memory stores information as trapped electric charge. And its biggest strength, its superpower, is precision. There's this technique called incremental step pulse programming that lets engineers program it to very, very specific values, one tiny little step at a time. But of course, that precision comes at a cost. It's pretty slow, it needs high voltage to write data, and it doesn't have the best endurance. All this makes it great for inference, which is just running an AI model where the core programming doesn't change very often. Okay, next up we have the ferroelectric FET, or FEFET for short. Let's call this one the Speedy Sprinter. This is a much newer, kind of more exotic technology, and it's built from the ground up for 2 things, speed and endurance. That makes it a really prime candidate for the super demanding task of actually training an AI model right on the chip. Now, instead of trapping charge like flash, a FEFET stores information in the actual physical orientation of atoms inside a special material. And switching them is incredibly fast. We're talking nanoseconds. Plus, it can be done billions of times without wearing out. On top of all that, it runs on super low voltage, which makes it extremely energy efficient. And our final contender is phase change memory, or PCM. I like to think of PCM as the malleable artist. It works by changing the actual physical structure of its material. It's a bit like turning water into ice and back again, but with a special kind of glass. So PCM stores data by switching a tiny piece of material between a messy, glassy state that has high resistance and an orderly, crystalline state with low resistance. This gives it a huge dynamic range, which allows for a lot of nuance. But its greatest strength, that malleability, is also its weakness. These states aren't perfectly stable, and they have a tendency to, well, change over time.
So let's just do a quick recap of our contenders. You've got Flash, the slow but super precise veteran. Then there's FEFET, the high-endurance sprinter built for speed. And finally, PCM, the malleable artist with that huge dynamic range. As you can see pretty clearly, there's no single perfect technology here. Each one comes with its own unique set of trade-offs between things like speed, endurance, and stability.
And this brings us right to the central conflict of this entire story. The incredible efficiency of analog computing comes from embracing the messy physical world. And what that means is that engineers are now in a constant battle against the inherent, totally unavoidable imperfections of nature itself.
Because there has to be a catch, right? I mean, if this is so great, why aren't all of our AI chips already analog? Well, it's because when you move from the perfect, predictable world of digital ones and zeros to the noisy, messy world of analog physics, you introduce one massive challenge.
And that challenge is called conductance drift. Simply put, these analog memories, they naturally forget. The values they're programmed to hold slowly change and decay over time. The best analogy is a photograph left out in the sun where the colors just gradually fade away. This fading of information is the single biggest hurdle for analog AI.
And look, this isn't a problem for just one of these technologies. Nope. All three of our contenders suffer from this drift, just for different physical reasons. In FIFETs, it's called depolarization. In Flash, it's charge literally migrating sideways. And in PCM, it's that glassy structure slowly relaxing into a more stable state. So the billion-dollar question becomes, how do you build a reliable computer out of unreliable parts?
Well, engineers are tackling this problem head-on with two really brilliant strategies. The first is about building smarter, and the second one is about working together. Let's take a look.
Okay, solution number one is to go vertical. Instead of building these sprawling single-story chips, engineers are figuring out how to stack memory layers on top of each other, just like building a skyscraper instead of a suburb. This 3D vertical stacking dramatically increases the density and performance without actually making the chip's footprint any bigger.
But of course, building a skyscraper of memory creates its own new physics problems. For example, how do you make sure a material crystallizes perfectly and uniformly all the way down a deep, super narrow trench? This has led to some amazing innovations, like using new channel materials, things like indium gallium zinc oxide, or IGZO, which helps stabilize these tall vertical structures and really improves their performance.
The second big solution is all about collaboration, because technical innovation alone just isn't going to be enough. As one research paper puts it, for analog AI to truly succeed, the entire industry needs to agree on a common language, a whole new set of rules for this new type of computing.
So what does this new rulebook actually look like? Well, it means defining things like acceptable drift budgets, basically how much a value is allowed to fade before it's a problem. It means creating tiered retention classes for different uses, from a huge enterprise server down to a tiny Internet of Things device. It's really about creating a standard framework for a new kind of computing that is, at its heart, probabilistic, not deterministic.
And really, what this all comes down to is that the next generation of AI is being built on a completely new foundation. It's one that doesn't try to fight against the imperfections of the analog world, but instead understands them, manages them, and even leverages them to achieve this incredible new level of efficiency.
Which, it leaves us with a pretty fascinating final thought. Right now, this drift, this slow forgetting, is seen as a bug that needs to be fixed. But in biology, in our brains, forgetting is a feature, right? It helps us learn and generalize. So the question is, in our quest for ultimate efficiency, are we accidentally building computers that not only think, but in some small, fundamental way, also forget, just like we do?